All right, so let's jump into it. So today we're going to talk about the Gemma 3 tech report with a particular focus on the post-training side of things. I think at a high-level summary, the main sort of takeaway is that we've got models that are kind of on the medium small side, so from 1B to 27B parameters. They've got 128 token context, which is cool. And the sort of thing they emphasize is how they used some sort of knowledge distillation to get significant performance improvements, both during pre-training and post-training. But then they emphasize that their kind of recipe had like a huge impact on domains like math, chat, and so on. And so now we have these like Gemma 3 models. For example, the 4B is competitive with the Gemma 2 27B, and the 27B itself is now competitive with their kind of proprietary Gemini models or an older version of them. So this is like pretty exciting. And we can sort of, I think, skip straight to the post-training part to sort of see if we can understand what they did. So what I'll do is I'll maybe give like a quick high-level summary of this, and then we can dive into some of the specific questions. So first of all, they sort of talk about how they kind of blend a whole range of different techniques. This is kind of interesting because when you sort of read other papers, they tend to sort of emphasize like something very specific, like just using reinforcement learning or, using some offline method like DPO. But here they kind of really blend a bunch of stuff. So they've got like knowledge distillation, and this is not just like the conventional knowledge distillation. This is the sort of on policy kind of generalized knowledge distillation that DeepMind published last year. And they've also got this kind of sort of mix of different RL methods that they use to kind of improve, I think, or mitigate elements of reward hacking. And now they've also got some references for like specific domains, how they kind of treat them. So for example, when they're doing like human preference modeling, they use these like weight average reward models. But then when they do like code, they're using code execution feedback. And for things like math, they're using kind of ground truth rewards, which is pretty popular now, as we've seen since the release of like DeepSeek R1. The other things that sort of stood out to me was like a pretty big disclaimer about the BOS token. I think if you remember, like with the original Gemma models, when they came out, a lot of people kind of had trouble figuring out how to fine tune them. And it was partly related to the way that like the BOS token needs to be added to the sort of training samples. And so they give an example here where if you basically want to have some sort of dialogue like between a user and a model, you need to populate it with the standard kind of start of turn, end of turn things that we've seen in other models. But crucially, you need to append an actual BOS token like explicitly, like without doing the tokenization, right? So you don't want to tokenize a string, you just want to add it as a single token. And this actually turned out to be also quite important in the earlier models. And I guess now they're really trying to make sure that people pay attention to that. So in terms of results, they sort of highlight how the 27B model is ranked 9th on LMSys, which is pretty impressive because, compared to say DeepSeek V3, this is kind of like a 600B parameter model. Well, it's a Mo, so it's not easy to compare, but still, it's kind of better than this, which is impressive. But it's also much better than, for example, MetaLlama 405B. So models that are roughly 20 times its size, it's doing much better on. The thing that was a little bit, I think, sort of tricky is sort of in the evals, they kind of deliberately only compare to themselves. So they only compare the kind of diff between like Gemma 2 and Gemma 3. And they make the observation that they did this because it's not fair to compare, different models under different evaluation settings. which, I can understand, but it also makes it now a bit trickier to sort of have a quick idea of like, how well does this model stack up against, for example, Quen 2.5. And so I had a quick look at the Quen 2.5 report, and I think we can sort of see that the 27B model is kind of on average comparable to Quen 32B. But in some domains, like for example, coding, so you've got live code bench, the Quen models are typically much stronger on that. So this was like the one thing that made it a bit tricky to compare. So maybe at that point we could sort of dive into the discussion. What did you guys find interesting about this paper?
Well, yeah, I think the nice thing is the multiple methods, and I think, if I'm not mistaken, the warp paper then kind of blends the different outputs from the different RL techniques together. So
I think warp is about merging.
Reward.
No, it's,
okay.
I think warm.
Warm is about merging the reward models, and these are about merging the actual models, if I'm not mistaken. Yeah, let's have a look.
Yeah, so they say in like the abstract of this that here you are merging the policies during RL.
So they must have trained.
So well, it's a bit tricky because it's not like very let's say familiar for me. Instead of, well, you have this objective where you don't want the reference policy to diverge too much from the train policy. Instead of having this Kyle term for this method, they kind of merge at every step the initial policy with the train policy, and it can be seen as an encore that they merged this together to have this kind of encore. And I think that the same idea is used for well, so they don't train one policy, they train a batch of policies, and at each steps they use this spherical merging, I think, which is slurp. Yeah, I don't know if you have other points to write here.
Yeah, I haven't read this paper, but I guess intuitively it makes some sort of sense, right? Which is like usually when we do like PPO or any sort of RL thing, we always have this KL term, and what people often do is they specify some number of sort of training steps when they should kind of synchronize the reference model, right? So you might say, okay, after 100 steps, let's replace the reference model with the current policy. And I guess what warp is partially doing here is kind of continuously keeping the reference in sync, right? Through merging.
Yes.
Yeah.
Yeah, the other thing, like on this like knowledge distillation, I know a lot of people like talk about this on Twitter and stuff about, oh, this is like a super kind of cool popular technique, which is kind of finally getting, used. What's probably worth emphasizing is that this type of knowledge distillation that Google is using for post-training is not the kind of naive, simple thing where you just have like a teacher and a student and you just basically don't update the outputs that you're training on. So you have some sort of fixed data set usually of teacher outputs, and then you just train the student to kind of match the outputs of the teacher. Whereas in this nice paper from Google last year, they actually do kind of online knowledge distillation, and they showed here that they got significant gains from doing that. And Kashif actually added this to TRL last year. So if people want to try it, you can look up the GKD trainer.
I was curious, they mentioned that they do distillation from a large instruction fine-tuned teacher, but do they specify which model that is?
No, I suspect it must be some variant of Gemini.
Yeah, just a question here. So maybe I'd like some key knowledge about this, but they mention at some point that a common finding is that to train a small model, it's preferable to distill from a smaller teacher. Is it like a widely known thing?
Yeah, so this is discussed partly in this paper, but it's also in other papers where basically there's like a kind of capability mismatch or capacity mismatch. So if my teacher, let's say, has 100 billion parameters and my student has 1 billion, then if I'm trying to solve, for example, math Olympiad problems, maybe my 100B teacher is capable of doing that, but the 1B has basically no chance of like modeling that distribution. It just doesn't have sufficient capacity. And so what motivated this particular work was the idea that if you are like kind of continuously generating outputs from the student, which are then kind of being corrected by the teacher, this is letting the kind of the student get a kind of better modeling of the underlying distribution, despite the capacity mismatch.
Okay, thanks. So they are. So we've spoken about warp. So they're saying that they use an improved version of these three algorithm: bound, warm, and warp. Bound and warm are a bit simpler, in my opinion, than warp. Bound is basically you sample a batch of completions from the policy, you select the best one, and you fine tune on this one. So it's kind of like the same as best of n sampling, but at inference time, you get the motivation is that you get directly the best of n instead of having to sample the batch of completions.
Oh, this is cool. So this is kind of like you know these whole things about training in the latent space, like with chain of thought. It's kind of in that flavor where instead of having to spend all the computer inference time with best of n, you just try to learn it.
Yeah, and at inference, I think that you don't need this reward anymore. So, yeah.
Oh, that's cool. Maybe we should read this next week because it looks like a pretty cool idea. And if I'm not mistaken, oh yeah, sorry.
Oh, sorry. I just have a question for you, Lewis. It might be basic, but my question is like for what you described about teacher-student model. What if the student model that is getting corrected by the teacher model based on the data set and based on the knowledge it has? What if for a specific like completion it comes out of distribution? So like it's not it's not resolvable by the small model. So there is no there is nothing inside the distribution of the student model to come up with answer so that like the bigger model can kind of like resolve it. So what do people do in that scenario?
Yes, good question. I'm not sure exactly what people do when it's like kind of out of distribution. I mean, I suppose it's like so you're sort of asking the question of like what happens if I give the sort of student a prompt which is sort of wildly out of distribution for the student, but perhaps the teacher
Yes.
it's like in distribution. My suspicion is that if you were using like an online method like GKD, the student would emit some sort of garbage, right? Like some hallucinated stuff. And the teacher would still be able to give you some kind of feedback. to potentially correct that. I don't know if you can magically make it in distribution, but it potentially would help. I mean, maybe Kashif has some intuition here too.
Yeah. So one could also augment the distillation loss with supervised loss, weighted supervised loss on the generations from the teacher with respect to the student. Maybe it's not done in this method in GKD, but I believe there is another kind of variant that adds to the GKD loss plus a weighted supervised loss with respect to the generations from the teacher. And that way you're also pushing, but you're also anyways pushing the logits towards the teacher one. And because you said the teacher is, for the teacher, the prompt is in distribution. So it's kind of also kind of learning with respect to that.
Yes, that's true. But so back to the Levis explanation. So
Mhm.
imagine the small model is generating some nonsensical things. So
Mhm.
then, would it be would it make it at risk of the bigger model to kind of like solve or correct the nonsensical output of the smaller model, get into another direction, so like going
Mhm.
far off from the original prompt, based because the bigger model is kind of correcting based on the output of the smaller model, and the output of a smaller model is something totally nonsensical, like out of distribution. So how the bigger model can understand the original prompt which was asked, so that it can output like the overall output would be sensical.
Right. So as far as I know, in these methods, there's no direct connections in terms of the teacher and the student model with respect to like gradients. It's
Mm-hmm.
only the outputs are treated as the outputs from the student, and the teachers are kind of treated as like a new data or data over which then you update the teacher model weights. So
Mm-hmm.
sorry, the student model weights.
Yeah.
Um,
Okay.
and so
Yeah,
it
so
will, I guess.
maybe one way of thinking about it, Stu, is like you've got these kind of distribution over the logits for both of these models. And, even if those distributions are like kind of perhaps wildly separated, the hope is that with this like kind of on-loan methods, you gradually bring them closer. I mean,
Yeah.
there's probably not going to be perfect overlap. But yeah, for the specific case of an individual prompt, I'm not exactly sure what would happen, but perhaps if you just looked at like just the evolution of these logic distributions, you would see them
Correct.
kind of gradually evolve. It's a
Okay.
good question,
Correct.
though.
Thank you.
So we have this last method, warm, which is, well, if you have the paper, yeah. I don't know if you guys have read the paper here, but it's kind of the same idea. The only, let's say, new idea here is that you have a reward that you have a multiple rewards. Well, you have a rewards model that has been fine-tuned with different hyperparameters. So you get this batch of reward models, and for each reward model, you can get an individual reward, and then, as far as I understand, you weight you sum this reward to get an average of all these rewards model, and you use it as a reward for the online methods. So the idea is quite nice. I guess it has something to do with the stabilization of the learning, I guess. I did not dig into the details of the paper, but yeah, this is one of the three methods that they merge and improve to get this RL post-training pipeline in Gemma 3.
Yeah, I mean, this is actually pretty cool because, like, you know, you often see when you do any sort of like RL that, like, in your like learning curve, you'll get like rewards going up, and then there's like some hack, like the model figures out like how to hack one of the reward signals.
Yeah.
And I guess by doing this averaging, you're sort of making the model like more robust so that the reward signal is not just fixating on like something weird, like, you know, the word JavaScript. So, and also I think what's cool about this is like, I don't know for sure, I haven't read the paper, but I wonder if like you can train multiple reward models on like different data sets. So it's not just different hyperparameters, but you can, I wonder if they're training like, you know, reward models for like helpfulness, reward models for like, you know, harmlessness, and then just merging them together. Because I remember in Llama 2, they had to have like kind of two reward models in play. And if you can just have kind of one universal one, that's pretty nice.
Yeah, well, the intuition behind, I guess, is it's easy to hack one reward model, but not like 10 simultaneously. So
Yep. Yeah, I think like these kind of things at some point would be interesting to explore, like on the TRL side. So, you know, I don't think this can probably be done offline, I assume. I'm not sure. Did you know if the weight averaging happens like you have a batch and then you feed it through multiple models, or is it happening like offline and then you just have like a single reward model that you're then feeding in?
I don't know. I guess it's offline, but I'm not sure.
I would
Okay, so it says actually here they were trained on the
offline.
same preference data set. Yeah. Yeah, maybe it would be interesting for us at some point to explore like you know, some like recipes for like merging these reward models. Just to get a feel for like, you know, does this stabilize training? Because, you know, right now us and everyone else is focusing on these like kind of verifiable rewards. But at some point you probably want to put into the equation like a standard reward model, and here this could be quite useful.
Yeah, probably. And we can imagine that having this merged model can be directly used with other verifiable reward functions within an online method like gRPO. Like it's already supported.
There is one paper I just want to highlight. Oh, sorry. Sure.
No, go ahead.
I'm going to change topics. So if you want to talk about model merging, now is your time.
Okay, so yeah, for sure. So my question is like for the mix of different rewards too. So are you telling that is it like a mix of reward for both verifiable and non-verifiable tasks? Like, does that work?
Yeah, so the way that at least like DeepSeek one was trained was like you have a prompt, and we have a batch of prompts, and some of those prompts may be for mathematics, for coding, and for those you would use reward functions. But some of those prompts might be like human preference questions, like, you know, I want to write a poem about blah, and then the model has to generate it. And for those, you would then use a reward model to give you the score. The question that is a bit unclear, right, is you now have multiple reward signals, and how you balance them and how you weight them is an open question, at least for me.
Yes, that. I mean, that was my question. You just put it in very straight forward way. Yeah.
Yeah, like I think one of the things we definitely want to do on the TRL side we discussed was like having the kind of ability to, you know, have this batch of prompts with these different like kind of reward functions, and then kind of selectively, you know, compute the rewards. So I think fairly soon we will start testing this.
Okay, can I have a follow-up question on that? So
Yeah,
would
of
it
course.
like having different type of reward models? So because the reward, I assume that reward models for verifiable tasks like math coding are, I believe, simpler than the ones for non-verifiable tasks. So
Mhm.
like merging these techniques together, would it be like additional load for like memory, or how can we like that my question is like the part that I don't understand is like how can we balance all these rewards like in
Mhm.
a single like pipeline?
Yeah, so engineering wise, it's probably going to get a bit hairy, but basically, like if I have
Yes,
a reward function, so if it's like mathematics, it's fairly straightforward. I just,
yes,
compute a string match. If it's code, I need to send my program to some sandbox and then get the
yes,
response. And that can be a bit kind of messy because maybe the program takes a long time to execute and, I'm just waiting for the answer. So you have to have some like efficient way of doing that. And then those two things are like kind of, let's say, like remote kind of sort of servers of sorts. Like in terms of memory, it's basically zero. The big problem, of course, is the reward model. So now you've got a reward model in the mix. And what we've done like conventionally with like PPO is we basically shard the reward model across like all available GPUs, and
mm.
then we also
Oh,
shard the policy. Um, the downside, of course, is like you pay a price in memory. So like already we know that like doing like GRPO is quite memory intensive, especially if you're doing like very long context.
yes,
And so I would say from an efficiency perspective, probably what you'd want to have is the reward model hosted on some endpoint, and then you just have a reward function which just calls the endpoint. Um, that would probably be the most memory efficient way to do it.
okay, great, thank you.
Yeah, so the last thing I wanted to say was like there's this nice reference to code execution feedback, and the paper is from Meta, and it's this RLEF paper. And what's really interesting about this is like this is kind of relevant to the Olympic coder work we just did recently. But they talk about how there's like a kind of special setup you can do for like RL with code that kind of gives you like significant performance improvements. And so the main thing they sort of show is that you really want to have the models be able to kind of do like kind of iterative debugging. So, if you give them a problem, like here, provide some Python solution, perhaps the first piece of code they give you is wrong. And so you feed it through some set of public test, and then you get some execution feedback, which is like, okay, your code failed the following tests. So now the model has the context of both the solution it submitted, but also the code, the tests where it failed, and then it can try again. And then eventually you'll get some like number of public tests passing. So you'll have some number of iterations you let the model do. And then what's kind of novel about this is that once those tests pass, you then feed them through a second set of private tests, and those are the ones that are used to actually give you the final reward that you then use for the RL update. And that's pretty cool because they talk about here that where is it? I'm trying to find it. Yeah. So they say we crucially utilize two sets of tests, a public test and a private test. And they talk about how basically if you have a private test set, it actually prevents the model from doing a very simple reward hack where it can see the test right from the feedback, and then it can just return the solution as the kind of desired output. And so it basically just learns how to copy the test rather than how to actually solve the problem. So that I thought was like pretty cool. And then they show the way they define their reward function. Like most of the way we've done this so far is like just using correctness as like the measure of reward. But here they also have like a kind of weighting where if the kind of action or the output doesn't have valid code, then you get like an additional negative reward. So this kind of thing I think would be kind of cool to incorporate into like GRPO, all the stuff that we're doing. And the other thing they show, which is like pretty impressive, is like the gains that you get from this method. So here you've got like Llama 3 8B, which on like the validation and test sets gets like kind of like 4%. And then if you add this RL, it kind of triples its performance, which is like pretty impressive. And then they show like a couple of different variants involving like the newer models. But I thought this paper was like pretty exciting and interesting as well. And perhaps that's also for me, like what I found cool about the Gemma paper is not so much the details they provided, but that they kind of provided links to other interesting papers.
So wait, in the method, like, what if the code doesn't pass the private test? It is used, but with a negative reward, right?
Correct. Yeah, correct.
Okay.
Yeah, so it's basically here. So, oops, where's the reward function?
Yeah, with the 1, -1,
Yeah.
and minus 0.0.
Yeah.
Okay.
Exactly. So in order to get a positive reward, first of all, you have to pass all the public tests because that's the only way you make it to the private test. And then if the private test passed, then you get a positive reward.
And if it doesn't pass the public test, it is just discarded. Like, it can be seen as online filtering on the prompts that are currently solvable by the model. Is it like you understand it?
Yeah, I think so. Like,
Okay.
if I recall correctly, yeah, so episodes terminate when public test evaluation succeeds or a specific step limit is reached. So I suppose if you don't succeed, you just get -1 because you reach the end of the episode, right? So you didn't make it past the public tests. And if you do, and you still pass all the private tests, then you get a positive reward. So it's a pretty strict filter, right? As you say.
Yeah.
Like getting to this like private test is it's a pretty cool approach. All right. Any last words on Gemma 3?
No, I'm trying to fine tune some of the checkpoints that they have with SFT and GRPO. It's quite cool to mix these very recent methods to see how they work together. So let's see.
Are you doing it on the 1B or the 4B?
12 and 24B.
Ah, okay. Wait, there's a 24B?
Yeah, I think so.
I thought it was 27.
No, 27.
27. Yeah.
Sorry.
Ah, okay. Cool. Yeah, nice. All right. Shall we call it a day then?
Yeah, see you later.
Bye, everyone.
Thank
Thanks.
you.
Bye.